Hi, I'm Ling Fang. I'm doing the report for Lab 2 collaborative experiment. The objective of this is to determine the latent heat or the enthalpy of water when it's vaporizing. So we can use the collaborative equation to find the relationship between them. So this is the equation given in the manual. So that's the dPdt, that's the latent heat H. And this T as specific volume, and we can use ideal gas law to change the specific volume to pressure and temperature with a gas constant. Now be careful, the gas constant here is actually vapor gas constant instead of the ideal gas constant, and the units in this need to be consistent. Here's the derivation of this equation. That's a dPdt. Now we can find the relationship between the latent heat and the temperature and pressure. So this a small manipulation of the equation, and we got this nice little equation here. It's a T, a P, and the main objective of this lab is to find the dPdt. And there are three procedures to find the dPdt. One is by using a local derivation, and this has a very large error. Later I will show. And the second one is actually to find a curve fit or like an exponential fit, and you use the equation to find the derivative. And the third one I will explain later. And here I go over the apparatus a little bit. That's the pressure sensor, that's the thermocouple, and here is the intake for drawing all the air out into a water pump system. And here is the heating station over there, and here's the water pump printer. Now here, let's talk about the data we collected. Here's temperature versus pressure, and this is the one whirling without the whirling beads. And here you can see a little dip in here because if I remember correctly, the TA had to adjust the thermocouple a little bit, and I think that upsets the data a little bit. And I will show how to interpret this later. And this is a pressure temperature curve with boiling beads. It has a much smoother curve because it wasn't disturbed. But if that means it's a good stuff, we still need to know. Now here is could be small, but that's the comparison of this data. This one is without boiling beads. This is with the boiling beads, and this is where I got the data from the steam table. And you can see they have a very nice little trend showing here. So then that's okay. It means that we got at least a reasonable amount of data, but with good behavior. But at the 60 Celsius, before the 60 Celsius, it's actually where the data are not considered to be reasonable, because you see here the 60 is at 20 kPa, and here at 60 is about 20. But below that, it's not good enough because we couldn't draw the pressure inside the flask to be lower enough to be able to bang. Okay, here, let's go back to the how to find the dPdt in order to find the latent heat. Okay, thank you. So you see before 60, this is just taking the local derivative just to take a bunch of data. Let's say that was 1500, so like I took about 1 to 10 or 1 to 50 as like the delta x, delta y, the range, and just straight up took the slope of it. And it was very jumpy, and it's not accurate. It's quite ugly, and you can see that before 60 degrees, these are just not reasonable. And so the better way that they do this is to actually find the curve, excuse me, to curve the graph, and we can find the local derivatives by that way. And it looks much neater, and I cut it before the 60. And here's the one without boiling beads, this one with the boiling beads. And here still using a local derivative curves. And the second one I actually used is to find the curve fit equation. There's a trend line with an exponential curve, and it shows the function. Now we can actually take the derivative straight out from the function, because it's pretty easy to do, and then we can find the dPdt straight out from that, and then just plugging all the numbers in there. So they look still similar, and so it's not helping that much, but it's a small improvement. The third one, before we get into the third one, we can see that the relationship between the latent heat and temperature is quite linear, so we can safely assume that it could be assumed to be like a linear function like this. Thank you. After a little derivation, so we can find a very nice equation like this. Why do we need that? Because we can use the Excel regression function in the analysis two-pack to find all the coefficients of this type of equation. And after that, we can just plug in the A's and B's into this to find a nice relationship between the latent heat and temperature. That's all that. And here is the regression curve. It still looks similar, and as a comparison, here's without B's. Now the last one has much closer to the actual steam table numbers, and the same as the with B's. And this one actually converges to a steam table, which is very nice. I was surprised, but that's it. And so the conclusion for this lab is that I learned a lot about the Excel sheet, I learned a lot about the regressions, and learned how to use the Clark equation to find these questions.
What is the advantage of using beads?
You can go back here and look. Specifically like this. This one is without beads, and it has actually quite the same trend line. Well, the reason for using a bead is the boiling bead is to make the boiling much smoother, and if there's any disturbance and if the bottom is smooth, so there could be a certain shock boiling, and then they will kind of mess up the sensors a little bit, and that's not desirable because boiling beads will create nuclear sites for water to vaporize in everything, so less sensitive.